Welcome back to another Sleepy Steve story. Before we drift off tonight, remember to subscribe to help Steve-O out, and I will keep making more sleepy stories to help you study gently, revise quietly, and settle your mind at the end of the day. Tonight, we are staying in Unit 3 Chemistry, Area of Study 2, and we are continuing to think about how chemical processes can be designed, controlled, and optimized. In the last episode, we looked at reaction rates and collision theory. We thought about particles moving, colliding, reacting, and sometimes failing to react because the collision did not have enough energy or because the particles were not facing the right way. Now we are going to slow the chemistry down in a slightly different way. Tonight's episode is about equilibrium and Le Chatelier's principle. You might picture a quiet industrial chemistry control room in the evening. Outside, pipes run carefully between tanks. Inside, small lights glow on a panel. The room is calm. Nothing seems to be happening quickly. But inside the reaction vessel, particles are still moving. Reactants are forming products. Products are forming reactants. Forward and reverse reactions are occurring at the same time. And even though the system may look still from the outside, it is quietly active on the inside. That is the central idea of dynamic equilibrium. A chemical system can appear constant, while particles continue reacting in both directions. So take a slow breath in and a slow breath out. Let the control room become quiet. Let the reaction vessel settle into your imagination. And let us begin with reversible reactions. A reversible reaction is a reaction that can proceed in both directions. The reactants can form products, and the products can react to form the original reactants again. In a chemical equation, a reversible reaction is shown with a double arrow. The forward reaction moves from left to right. The reverse reaction moves from right to left. For example, in many industrial reactions, reactant gases are placed into a closed vessel, and under suitable conditions, they begin to form products. But as soon as some product has formed, some of that product may also begin to react back into reactants. At first, the forward reaction may be faster because there is a high concentration of reactants and very little product. The reactant particles collide often and product begins to form. But as time passes, the amount of reactant decreases and the amount of product increases. The forward reaction slows down because there are fewer reactant particles available. The reverse reaction speeds up because there are more product particles available. Eventually, in a closed system, the forward and reverse reaction rates may become equal. When that happens, the system has reached dynamic equilibrium. Dynamic equilibrium does not mean the reaction has stopped. This is one of the most important exam ideas. At equilibrium, the forward reaction and the reverse reaction are still occurring. They are simply occurring at the same rate. Because the rates are equal, the concentrations of reactants and products remain constant over time. Constant does not mean equal. The concentration of reactants does not have to be the same as the concentration of products. It only means each concentration is no longer changing because the forward and reverse reactions are balanced in rate. This is why we call it dynamic equilibrium. Dynamic means moving or active. Equilibrium means there is a balance in the rates of the forward and reverse reactions. A strong VCE chemistry answer should say both parts clearly. At dynamic equilibrium, The forward and reverse reactions continue to occur at equal rates, so the concentrations of reactants and products remain constant in a closed system. Now let us pause on the idea of a closed system. A closed system means matter cannot enter or leave the system, although energy may be exchanged with the surroundings. This matters because equilibrium can only be maintained if reactants and products are not escaping from the reaction vessel. If gas escapes, or if product is removed, the system is no longer maintaining the same balance of particles. In the quiet control room, imagine the reaction vessel sealed. The particles inside collide, react, change direction, and react again, but they do not leave the vessel. That sealed space allows equilibrium to be established. Now we can think about equilibrium position. The equilibrium position describes the relative amounts of reactants and products present at equilibrium. If the equilibrium mixture contains a high proportion of products, we say the equilibrium position lies to the right or favors the products. If the equilibrium mixture contains a high proportion of reactants, we say the equilibrium position lies to the left or favors the reactants. This language is very useful in Unit 3 chemistry. When a change is made to an equilibrium system, we often explain whether the equilibrium position shifts to the right or to the left. A shift to the right means the forward reaction is favored and more products form. A shift to the left means the reverse reaction is favored and more reactants form. The idea of equilibrium position leads us to the equilibrium law. For a reaction at a fixed temperature, the relationship between the concentrations of products and reactants at equilibrium can be described using an equilibrium constant, usually written as Kc. For a general reaction, where A plus Bb forms Cc plus Dd, the equilibrium expression places the concentration of products on the top and the concentration of reactants on the bottom. Each concentration is raised to the power of its coefficient in the balanced equation. So the expression is C to the power C multiplied by D to the power D divided by A to the power A multiplied by B to the power B. In spoken form, that sounds a little long, so let the idea stay simple. Products over reactants, each raised to the power of its coefficient. Only species that appear in the equilibrium expression are included. For many VCE chemistry contexts, pure solids and pure liquids are not included in the Kc expression because their concentrations are treated as constant. A large Kc value means the equilibrium mixture contains a relatively high concentration of products compared with reactants. So the reaction is product favored at that temperature. A small Kc value means the equilibrium mixture contains a relatively high concentration of reactants compared with products. So the reaction is reactant favored at that temperature. Kc is temperature dependent. This is another important exam point. Changing concentration or pressure may shift the equilibrium position, but it does not change the value of Kc if temperature remains constant. Only a change in temperature changes Kc. This is because temperature changes the relative extent of the forward and reverse reactions in a way that changes the equilibrium constant itself. Now we can introduce the reaction quotient, Q. The reaction quotient has the same mathematical form as the equilibrium expression, but it can be calculated at any moment, not only at equilibrium. Q tells us whether the current mixture has too many products, too many reactants, or is already at equilibrium. If Q equals Kc, the system is at equilibrium. If Q is less than Kc, there are relatively too many reactants and not enough products, so the system will shift to the right, favoring the forward reaction until equilibrium is restored. If Q is greater than Kc, there are relatively too many products and not enough reactants, so the system will shift to the left, favoring the reverse reaction until equilibrium is restored. You can think of Q as a quiet check of the current mixture. It looks at the reaction vessel and asks, compared with the equilibrium constant, are we product heavy, reactant heavy, or balanced? This can be useful in exam questions where the concentrations are changed and you need to predict the direction of shift. Now we arrive at Le Chatelier's principle. Le Chatelier's principle states that when a system at equilibrium is disturbed, the system will partially oppose the disturbance in order to re-establish equilibrium. The word partially matters. The system does not usually remove the change completely. It responds in a direction that reduces the effect of the change. It is like a calm balance trying to settle again after being gently pushed. In Unit 3 Chemistry, the main disturbances we usually consider are changes in concentration, pressure, and temperature. We may also consider the effect of catalysts, but catalysts do not shift the equilibrium position. They only help the system reach equilibrium faster. Let us begin with concentration. If the concentration of a reactant is increased, the system responds by using up some of the added reactant. It does this by favoring the forward reaction. The equilibrium position shifts to the right and more product forms. If the concentration of a product is increased, the system responds by using up some of the added product. It does this by favoring the reverse reaction. The equilibrium position shifts to the left and more reactant forms. If a reactant is removed, the system responds by replacing some of the removed reactant. It favors the reverse reaction, shifting left. If a product is removed, the system responds by replacing some of the removed product. It favors the forward reaction, shifting right. This is why removing product can be useful in some industrial processes. If product is continuously removed, the equilibrium system may respond by producing more product, increasing yield. But in a real industrial setting, the choice is not always simple. The cost of separating products, the rate of reaction, the energy required, safety, equipment design, and sustainability all matter as well. Now let us consider pressure. Pressure changes are most relevant for reactions involving gases. If the pressure of a gaseous equilibrium system is increased by decreasing the volume, the system responds by favoring the side with fewer gas particles. This reduces pressure because fewer gas particles in the same space produce fewer collisions with the walls of the container. If the pressure is decreased by increasing the volume, the system responds by favoring the side with more gas particles. This increases pressure by producing more gas particles. To apply this in an exam, first count the moles of gas on each side of the balanced equation. Then decide which side has fewer gas particles and which side has more gas particles. If pressure increases, equilibrium shifts toward fewer gas particles. If pressure decreases, equilibrium shifts toward more gas particles. If there are equal numbers of gas particles on both sides, changing pressure by changing volume will not shift the equilibrium position. This is a common place for careful thinking. The system can only reduce or oppose the pressure change by shifting if one direction produces a different number of gas particles. Now let us consider temperature. Temperature changes are different because they change the value of Kc. To apply Le Chatelier's principle to temperature, we treat heat as if it is part of the reaction equation. For an exothermic forward reaction, heat is a product. For an endothermic forward reaction, heat is a reactant. If the forward reaction is exothermic, increasing temperature is like adding heat to the product side. The system responds by using up some of that added heat, so it favors the reverse, endothermic reaction. The equilibrium position shifts to the left, and the value of Kc decreases for the exothermic forward reaction. If the forward reaction is exothermic and temperature is decreased, the system responds by producing more heat. It favors the forward reaction, shifts to the right, and Kc increases. For an endothermic forward reaction, the pattern is reversed. Heat is a reactant. Increasing temperature adds heat, so the system favors the forward, endothermic reaction, shifting right and increasing Kc. Decreasing temperature removes heat, so the system favors the reverse reaction, shifting left and decreasing Kc. A helpful exam habit is to identify whether the forward reaction is exothermic or endothermic before predicting the effect of temperature. Then use Le Chatelier's principle to decide which direction opposes the temperature change. Now let us think about catalysts. A catalyst provides an alternative reaction pathway with a lower activation energy. In an equilibrium system, a catalyst increases the rate of both the forward and reverse reactions. Because both reactions are sped up, the catalyst does not favor one side over the other. It does not change Kc. It does not change the equilibrium position. It does not change the final yield at equilibrium. It simply allows the system to reach equilibrium faster. This is very important in industrial chemistry because reaching equilibrium faster can make a process more economically useful, even if the final equilibrium yield is unchanged. Now we can connect equilibrium back to reaction rates. In the previous episode, we looked at factors that affect the rate of reaction, such as concentration, temperature, pressure, surface area, and catalysts. In this episode, we are also thinking about yield and equilibrium position. Sometimes a change that increases rate may not improve yield or may even reduce equilibrium yield. For example, increasing temperature usually increases reaction rate because particles have more kinetic energy and more successful collisions occur. But if the forward reaction is exothermic, increasing temperature shifts equilibrium to the left and reduces product yield. This creates a compromise. Industrial chemists may use a moderately high temperature to achieve a reasonable rate, even if a lower temperature would give a better equilibrium yield. They may use higher pressure if the product side has fewer gas particles, but very high pressure requires expensive equipment and safety controls. They may use a catalyst to increase the rate without changing the equilibrium position. They may remove product as it forms to encourage further product formation. This is the heart of optimization. Chemical processes are designed by balancing rate, yield, cost, safety, energy use, and environmental impact. Now imagine the control room again. A chemist looks at the reaction vessel. The temperature is steady. The pressure is monitored. The concentrations are measured. The catalyst is present. No single decision is made in isolation. Every condition affects the process in a particular way. A strong VCE chemistry response explains the change, the system's response, the direction of shift, and the effect on the amount of product or reactant. For example, if the concentration of a reactant is increased, the system partially opposes the increase by favoring the forward reaction, which uses up some of the added reactant and forms more product, shifting the equilibrium position to the right. That sentence has a clear chain: change, response, direction, effect. For pressure, a strong answer might say that increasing pressure by decreasing volume causes the system to favor the side with fewer gas particles, reducing the pressure and shifting the equilibrium position toward that side. For temperature, a strong answer must include whether the forward reaction is exothermic or endothermic. If the forward reaction is exothermic and temperature is increased, the system favors the reverse endothermic reaction to absorb some of the added heat, so the equilibrium position shifts left and Kc decreases. The more clearly you link the explanation, the stronger the answer becomes. Now, let us settle the main ideas. A reversible reaction can proceed in both directions. Dynamic equilibrium occurs in a closed system when the forward and reverse reactions continue at equal rates. At equilibrium, concentrations remain constant, but they are not necessarily equal. The equilibrium position describes whether the mixture favors products or reactants. The equilibrium constant, Kc, compares product concentrations with reactant concentrations at equilibrium, using the coefficients from the balanced equation as powers. A large Kc indicates a product-favored equilibrium mixture. A small Kc indicates a reactant-favored equilibrium mixture. Kc changes only when temperature changes. The reaction quotient, Q, helps predict which way a system will shift to reach equilibrium. Le Chatelier's principle says that a system at equilibrium will partially oppose a disturbance. Changes in concentration can shift equilibrium to use up or replace a substance. Changes in pressure affect gaseous systems by favoring the side with fewer or more gas particles, depending on whether pressure is increased or decreased. Changes in temperature depend on whether the forward reaction is exothermic or endothermic, and temperature changes also change Kc. Catalysts help equilibrium systems reach equilibrium faster, but they do not change the equilibrium position, Kc, or final yield. And now, the control room becomes quieter. The lights on the panel glow softly. The reaction vessel is sealed. Inside, particles still move. Some become products, some become reactants again. Forward and reverse reactions continue in a calm balance. And if the system is disturbed, it gently responds, shifting in the direction that partially opposes the change. That is equilibrium, not stillness, but balance. Not silence inside the reaction vessel, but equal rates, constant concentrations, and a system quietly finding its way back to stability. This has been Sleepy Steve. Sleep well and let equilibrium settle gently in your mind.